Okay, then maybe we start with our last talk, and it's a pleasure to introduce our last speaker, Marco Gualtieri from the University of Toronto, and he will speak about Brane quantization and generalized scalar structures.
Okay, thank you very much, and thank you for the invitation to this conference, which is a very interesting experience, especially under the circumstances. And I also thank the other speakers for giving such wonderful talks, and especially for leaving the blackboards so pristine that I can use them with perfect clarity. Okay, so this work is a joint with Francis Bischoff. And also partially with two other students that are working with me at the moment, Leonard Doppenschmidt and Yusong Jiang. And it's all to do with this alternative approach to generalized scalar geometry, which we found by trying to solve the problem of understanding the generalized scalar potential. Scalar manifolds have a scalar potential. The metric is determined by a single real valued function. There's a question about whether this is the same, this is also true for generalized scalar structures. And the physicists had an inclination or an inkling. They had an intuition that it should be, in fact, true that generalized scalar metrics are determined by a single function. But in order to see this, you need to view the structure in a different way. And when you view it that way, it turns out that the quantization problem becomes more clear, much more clear. So I just want to give you the idea of what is going on. So let's look again at Kahler geometry. It's all right, leave it, it's fine, yeah. Okay, so Kahler geometry. So we usually think of, right, so let me tell you about something you know very well, a Kahler metric, but let me tell it to you in a different way. So suppose we take the cotangent bundle of a manifold. Okay, so this is a real symplectic manifold. And so this, I have no structure on the manifold so far. Okay. Now I'm going to introduce a complex structure on the manifold. So let's suppose that I is a complex structure on M. This induces a complex structure, which I'll call I0 on Tm, T star M. So now we have the structure of a holomorphic cotangent bundle. So so this T star M now has, which has a holomorphic symplectic form, omega naught, which I could write as the real and imaginary parts like this. So this is now a holomorphic symplectic manifold. And I hope this makes sense. I'm using the complex structure on the manifold to get the real part of my holomorphic symplectic structure. The imaginary part is the canonical holomorphics, the canonical symplectic structure. So we have, on any complex manifold, its cotangent bundle becomes a holomorphic symplectic variety. No surprise there. Okay. Now I'm going to introduce a Kahler structure. So suppose that now F is a Kahler form on M. All right. So what I can do with this Kahler form on M is I could, this is a 1-1 form, the usual Kahler structure that you're familiar with, and I can pull it back. This will be a 2 form on T star M, a real 2 form. And what I could do is something called the magnetic deformation, where I can add this 2 form to this holomorphic symplectic form. And you add them together, it will modify the real part and leave the imaginary part alone. And when you do this, the result will also be holomorphic symplectic. I'll call that omega sub f. This is omega 0 plus pi upper star f. This is the magnetically deformed of the cotangent bundle, and this is holomorphic symplectic variety. If you do this by if you want to understand an example, if you do this for T star P1, I'll draw T star P1 like this, some kind of non-compact holomorphic symplectic variety. The zero section is a Lagrangian curve inside this holomorphic cotangent bundle. But if I take a Fubini-Studi form, if I take F to be the Fubini-Studi on P1, and if I do the magnetic deformation, then this T star P1 with omega 1, or with this magnetically deformed structure, this would be, this turns out to be an affine quadric. And so this is definitely not affine. You have a compact curve. This one is affine. So we have a deformation of the complex structure of the holomorphic cotangent bundle into another space. Maybe I shouldn't call that space T star P1. I'll call it maybe the twisted cotangent bundle, maybe T star sub F P1. Okay. Now, okay, so this is a construction of a space that I really want to discuss in detail. This twisted cotangent bundle. Twisted. So what is this twisted cotangent bundle? Well, as a complex manifold, or as a holomorphic symplectic manifold, it is a deformation of the holomorphic cotangent bundle. It's genuinely different, non-isomorphic to the original. And so, but it has some nice properties. In addition to being a deformation as a complex symplectic manifold, it's also, it retains a holomorphic action of the cotangent bundle on it. It still has fibers. It still has a projection down to the base. That projection is still holomorphic, just as it was before. And these fibers, which are abelian groups, they're vector spaces. It's a vector. This is a vector bundle. Right? These vector spaces act on these fibers. So these fibers are affine spaces for the vector spaces. This is an affine bundle. You could think of this as a principal bundle in the sense that the cotangent of P1, I could think of it as a bundle of groups, and this bundle of groups acts on this bundle of torsors over the group. So it has this structure of almost like a principal bundle. And this thing has a class. So if we take the class of this, the equivalence class or isomorphism class of this thing, it would have a class in, as a principal bundle. You could think of it as H1 of, let me put holomorphic here just to emphasize, would have a class in this group. Okay, so the idea here is that this affine bundle is a deformation of this one, which is obtained basically by chopping this thing up into open sets and regluing them by such an H1 class with values in the automorphisms of this thing. Why do I put omega 1 closed? It is because I'm thinking of this space as a holomorphic symplectic structure. And the one forms act on it by translation along the fibers. And it is when they are closed that we get a symplectomorphism. So the closed one forms are exactly the automorphism of this vector bundle thought of as a holomorphic symplectic bundle. So this thing has a class in here, okay? And that is the Kahler class. So this is the receptacle of the Kahler class. So we could say that this is the Kahler class. Okay, so so we've identified a strange way of thinking about the Kahler class. The Kahler class is an isomorphism class of holomorphic symplectic affine bundle. The equivalence class of that affine bundle, the classifying class of this affine bundle is what we want to consider the Kahler class. Okay, now if that's the Kahler class, oh, I see. So, so let's say that we have this T star F, omega F. So we fix a Kahler class. And then, you know, inside a Kahler class, you're hoping to find Kahler metrics. Kahler metrics are the things that live inside the Kahler class. So where is the Kahler metric here? Well, let's trace it back, you know, reverse engineering. So we started with the Kahler class. We used it to deform this canonical symplectic form into this deformed version, right? And then we produced this. So you know, if I remembered this zero section is still here. It's still a smooth section of this affine bundle, but this is not a holomorphic section anymore because I've modified the complex structure. But this thing is still there. And if I restrict this form to the zero section, well, the canonical form will vanish on the zero section, as it always does for the cotangent bundle. And this one will not vanish, and it will recover the Kahler form. So in here, the Kahler metric is a section, is a C infinity section of this bundle. Okay, and the one that we still have left over from the construction is the zero section, which, you know, if I just think of this as a holomorphic symplectic affine bundle, I don't have a zero section. There isn't really a zero section, but because I constructed it explicitly, I have that zero section. The zero section, L, inside this T star F. So what we have is this affine bundle, T star Fm, and inside it, we have this C infinity submanifold L, which is giving me exactly the Kahler metric. The Kahler metric is this Lagrangian. Well, I just gave away the hint. So let's take a look at what this submanifold is. So if we restrict the holomorphic symplectic form to this submanifold, what do you find? Like I said, you're only going to get this real two form F, and you won't get any imaginary part. So if I take omega F and restrict it to L, what I'll get is the real part gives F a Kahler structure, which is a symplectic form. And the imaginary part gives 0. So that means that it's Lagrangian. It's a Lagrangian inside here. Okay, so a real Lagrangian for this symplectic form, which remember is the canonical symplectic form on the cotangent bundle, the real canonical. Okay, so everything that I've said so far, this is a reinterpretation of Kahler geometry, in which the Kahler class is a holomorphic symplectic affine bundle up to isomorphism, and the Kahler metric is a cross-section of that bundle, that cross-section being Lagrangian with respect to the imaginary part and symplectic with respect to the real part of the ambient holomorphic symplectic structure. Everything that I just said is straight out of a paper of Donaldson from around 2000. He reinterpreted Kahler metrics in this way. Okay, and the really cool thing about this way of thinking is that you can kind of imagine, well, okay, I mean, first of all, you can think of a metric as being a Lagrangian submanifold. That's kind of interesting. But even better than that is that we know how Lagrangians infinitesimally deform. They infinitesimally deform by a generating function. The degrees of freedom in a Lagrangian submanifold is a function, a real function on that Lagrangian. And that function is the Kahler potential. So the reason that Kahler metrics depend on only one scalar function is precisely because the Kahler metric is a Lagrangian submanifold. It's a remarkable observation. Okay, so the reason that I'm telling you this old story of Donaldson is that this is the way of looking at Kahler metrics, which generalizes very well to generalized Kahler. And this is the way of thinking which gives rise to the correct interpretation of what a generalized Kahler potential function would be. It's also true that a generalized Kahler metric is a Lagrangian submanifold in a holomorphic symplectic variety. So that's the key part. Well, you could either think, that's right. I mean, you could either think that that given, so what Vesti asked was whether it should be thought of as an infinitesimal modification of the Lagrangian or an actual modification of the Lagrangian. And in this case, you could do either one. If you give me a closed one form or the derivative of a two form, right? This will act here by moving this Lagrangian up by this two form, or you could multiply it by h bar or t, whatever, right? And you could produce a family, and then you could take the derivative and say that it's actually a normal vector field. So you could think either way, because it's linear in this case, right? You could interpret it either as a normal vector, which is pushing your Lagrangian somewhere else, or you could think of it as an actual motion, which moves the Lagrangian to a different one, okay? And as long as this function is closed, as long as this one form is closed, you will not ruin the Lagrangian condition. This condition is an open condition. So as long as you don't move it a little, too much, it will stay symplectic and you're going to be fine. Of course, if you move it too much, then this symplecticity, this non-degeneracy of the real part may fail. And we're familiar with that idea. Okay, so what Donaldson called these things, these Lagrangian symplectic submanifolds, is he called them LS submanifolds. So generalized Kahler metrics are LS submanifolds in the twisted cotangent bundle. That's the statement of everything I've said so far. Okay, now, okay. So before I go to the generalized version of all this, I want to say one extra thing, which is about how to quantize this. How to quantize. Okay, so so we're going to try to understand the quantization of a Kahler manifold in this picture from this point of view. Okay, so how should we think about it? So usually we have to assume that F is the curvature of a unitary connection, right? So that requires integral periods, the quantization condition. And then what we do is we take the 0, 1 part, that gives a d-bar operator on some line bundle, which I'll call U0. And we get a holomorphic line bundle U0 over the manifold. And then what do? We produce a vector space, which is the sections over M of this U0. And that's the quantization, the Hilbert space, if you want. So that's the traditional way of thinking. Now, the alternative way of thinking using this procedure is that, so instead, we work not on M, but on T star M with its canonical symplectic form. This is a symplectic manifold, and this has an A model or Fukaya category. Okay, so where are we going to get this vector space? Instead of getting it from the B model of the complex manifold M, I'm going to get it from the A model of the cotangent bundle of the manifold M. Okay, so how do you do it? We have to observe that T star M has two objects. Okay. One of these objects is L, the omega Lagrangian. We know that Lagrangians are objects in the Fukaya category. The other object that it has is, I wish I could tell you that it had another Lagrangian submanifold, but unfortunately it does not have another Lagrangian. Instead, it has what's called a coisotropic A-brane, or what they sometimes call a space-filling brane. So let me write it this way. If we pull back U0, this line bundle, and if we equip it with the pullback of the of this pre-quantum connection, and if we add to it a one form, which is I star of theta, where theta is the canonical one form. Okay. What we get is a line bundle with unitary connection. Sorry, there should be a little I here to make sure that this is unitary. So this is a unitary connection on a line bundle over the entire cotangent bundle. This is over the entire cotangent bundle. Okay. And this is what is called a coisotropic A-brane. Okay. This is a concept that was discovered by Kapustin and Orlov. Okay, in 2000. They looked at mirror symmetry and they realized that if in the Fukaya category you only consider Lagrangian submanifolds, you will not get mirror symmetry. In order for mirror symmetry to hold between a complex manifold and its derived category and a symplectic manifold and its Fukaya category, you must include extra objects beyond the Lagrangian ones, and those extra objects are exactly of this type. Okay, and so here we have on this twisted cotangent bundle, or sorry, on the cotangent bundle, right, on the usual cotangent bundle of M, we have two objects, and so what we want then, I'm just afraid of using this board. Oh, I could use this one maybe. So this connection, this will have curvature, which is the real part of, this will have the real part of omega F. So that connection is built so that its curvature will be the real part of this. I'm sorry, it's because the curvature, I put this I here because I wanted this thing to have real curvature, okay? And the curvature is going to be the pullback of F plus I star omega, which is the real part of this thing. Yeah, okay, yeah. Okay, so, so then all that remains is that we get a vector space by taking the Hom between these branes, L and this pi upper star U. I'll call this B. This B, B. Sorry, this whole thing here, I'll call it B. Okay, and this is a homomorphisms in the A model. Okay, now this we're going to see how much time we really have. Homomorphisms between Lagrangians are under, they have been studied to death in the symplectic topology community. But when you put a coisotropic A-brane here, then everyone just runs away. They don't want to compute that. There's only 3 or 4 papers where such Homs in the A model have been computed. And it's always an ad hoc method. if you look in Witten-Kapustin or Witten-Gukov, or if you look at Aldi, Zaslow, they have ad hoc methods in very particular cases for computing this vector space. Okay, and so the way that I'm not going to go into great detail about this, but in our paper, we propose a method for computing this Hom, which involves converting this space-filling brane into a family of Lagrangians. So I can, for example, this is one option, although it's not the one we use in the paper, we can foliate the space-filling brane by the fibers of this affine bundle. These will be Lagrangian, holomorphic Lagrangian for omega f. And then this connection will be flat along them. And we could take flat sections along the fiber. That gives a sheaf here, and we could take the global sections of that sheaf along this, this Lagrangian. So we propose a method like this. We basically convert this into a family of Lagrangians. We take the Hom between the Lagrangians in a family, and then we take global sections over the family parameter space. That's the method that we propose to obtain this vector space. And any way that we have been able to compute it, it agrees with the holomorphic sections of U0. So at least we have a possible method for obtaining the right vector space, but not using the complex geometry of M at all, instead using the symplectic geometry of its cotangent bundle. Okay, and the final thing that I want to say is that this quantization, this is quite good, but personally, if you're a fan of algebraic geometry, the sections of a line bundle isn't really going to get you that far. What you're really interested in is sections of the line bundle, the square of the line bundle, the cube of the line bundle, and so on. And if you take the sections of all of those bundles, right, then you get an algebra. You get a complex algebra, a complex associative algebra, which is the algebra that you study in algebraic geometry. So if I wanted to do that, that's the last thing I want to be able to do inside this alternative viewpoint, is I want to be able to tensor this line bundle up higher and higher and produce all the sections and get an algebra. That's what I really want. So how would you get that? So question, what about the algebra? The algebra is usually, the algebra is usually, I don't know, I'll call it M as R as a ring. So it's a sum k greater than or equal to 0, h0 m u0 to the k. Right? So the question is, how could we obtain this? Well, this is quite interesting because this there's one last property of this affine bundle that we haven't used, and it is that the affine bundle, it has the ability to tensor itself, because it is, after all, a bundle. So, for example, if I have this T star F M, this fibers over M, right? And I can take the fiber product of this with itself. So I can produce TF fiber product over M with T star F. And this will be T star 2F. So there is a natural way of tensoring this holomorphic object, this holomorphic symplectic variety, right? You take the fiber product of it with itself, and then you will get another twisted holomorphic cotangent bundle with twice the Chern class, twice the Kahler class. So here what you see is this is explaining why Kahler classes form the Kahler cone, right? So this is the Kahler cone. Sorry. Yes, thank you. So what I really mean is, let me do it properly. You take T star F cross T star F. This is a symplectic manifold. Inside it, you have the fiber product. That is a coisotropic submanifold. And then there is a symplectic reduction, which goes down to T star 2F. So this symplectic reduction is a Lagrangian relation between the product and the one that has twice the Chern class. Okay, and this this is why we see that we have a Kahler cone. So Kahler classes are given by these affine bundles. The product of the affine bundles with themselves give the Kahler cone structure. Okay, and the cross sections of these things, which are Lagrangian, they give the Kahler metrics. Okay, yeah, and so it is because of this structure that we get a ring structure on these Hom spaces. These Hom spaces. So this gives rise to an algebra by taking Hom, taking a sum of Homs from L to B convolved with itself k times. Incidentally, I don't, this L, this Lagrangian, it has the special property that if you tensor it with itself, it gives itself, it's idempotent. So in any case, the point is that what I'm really using is that the cotangent bundle, this thing here, it has a natural addition. And this addition induces a monoidal structure on the Fukaya category. So this, the Fukaya category of the cotangent bundle of M has the ability to take objects and tensor them one with the other. And that is the reason why we get this algebra structure. Okay, so I would not have gone through this tortured, rewriting of everything you know about Kahler manifolds, except for the fact that this, all of this, goes through for generalized Kahler. So any questions about this before I explain kind of what the generalization looks like? No questions.
Do Lagrangians which are not graphs have any meaning?
They should. Well, they certainly certainly there are objects there. So I guess you could consider them to be kind of like some kind of generalization of Kahler metrics, but they don't appear in this story. But yeah, it's an interesting question. But of course, I mean, people study Lagrangian, the cotangent bundle all the time. It's an interesting thought.
Marco, may I ask something?
Yes, please.
Marco?
Yes, go ahead.
So this B star K, so is it contained in this, what you denote as a T K times F star? I mean, this kth power of B, which you just introduced. So
yes.
you wrote it as B.
This is a space filling brane on. That's right. So this would be a space filling brane on the cotangent bundle T star M. These objects, all of these objects, the sequence of objects B1, B2, B3, they're all space filling branes on the cotangent bundle of M. The symplectic cotangent.
How is it related to this reduction T star 2F, which you wrote in the middle blackboard?
Yeah, this is just another way of seeing it, because this T star 2F, it has a holomorphic symplectic form, but the imaginary part is just the usual cotangent bundle. And so you could think of this as being the usual cotangent bundle, but with a space filling brane on it, which has weight 2F, which has curvature 2F. So I'm just trying to indicate.
Is there an inclusion of this space B star to the power K? Is it contained in T star KF?
Yes, correct. Yeah.
Yes,
this is actually a space filling brane.
Yeah.
This is a space filling brane on that space. Yeah.
Okay. Thank you very much.
You're welcome. Okay. So let me just erase this and then explain what the generalization looks like. And let me do it by giving a little bit of an example. Okay, suppose that, and this is the example that we look at in great detail in our paper. So suppose that you have a toric Kahler manifold. And suppose that we have a pre-quantization L nabla for the Kahler structure. I'm sorry that I called it omega. Maybe I will try to just maintain my notation with F. Okay, so this is a toric Kahler manifold which has been pre-quantized, and there is a, let's say rho is the torus action, and suppose that rho hat is the linearization of the toric action. So I've lifted the torus action to the line bundle, which pre-quantizes this Kahler form. Okay. Okay, and this torus action, this lifts to the cotangent bundle of M. Of course, if it acts on M, it will act on the cotangent bundle. But the great thing about symplectic actions, you know, the great thing about this, actually, sorry, let me. Yeah, that's right. So this lifts the T star M, and there's a holomorphic moment map, which I'll call J sub, I'll just call it J. So T C star. This is the moment map of the action on T star M. Okay, and finally, I'm going to pick, this is how I'm going to deform this Kahler manifold. I'm going to deform the picture. So, you know, with this data, and you don't even have to worry about the torus action, with this data, you could implement everything that I talked about. But now I'm going to deform this thing to generalized Kahler. The way that I'll deform it is by choosing an R matrix. An R matrix is just a skew symmetric element in wedge 2 TC. It's something in wedge 2 of the Lie algebra. And I can use this, this action to push the bivector forward to get a Poisson structure on the manifold. So rho lower star of C is sigma, a holomorphic Poisson structure. And if I, right, and if I use the linearized action to push forward C, what I get is sigma hat C, which is a Poisson structure on the total space of L, which is usually called a Poisson module structure. Okay, and okay, so I'm in the middle of giving the deformation. So what I need now is the space that will play the role of the cotangent bundle, the space that played the role, that will play the role of the holomorphic symplectic manifold. I need to construct that space. So the holomorphic symplectic manifold, okay, is going to be actually very simple. It's just the cotangent bundle with its canonical symplectic structure. This is just the holomorphic cotangent. Okay, but it has a property. So, but I'm no longer going to be able to think of this as a vector bundle, and I'm no longer going to be able to think of it as an affine bundle either. It's going to be considered to be a Lie groupoid. So this has the structure of a groupoid. Yeah, let me just write down that structure just to show you how simple it is. So in other words, every point in the cotangent bundle, I'm going to think of it as an arrow which has a source and which has a target in the manifold. And this the target of a given point is a modification of just its projection down to the base. So if you just take a point inside the cotangent bundle and you just project it down to the manifold, you will get a point in the manifold. And that that is how we start off to figure out the target of this arrow. But actually, it must be modified in the following way: e to the 1/2 c j of z. So the moment map will take this point in the cotangent bundle to something in the dual of the Lie algebra. Then this bivector will act on that dual element and give me an element in the Lie algebra. And that Lie algebra element, I can exponentiate it to a torus element, and that torus element moves this point. It moves it, let's say, forward by a unit 1/2. And the source is going to be exactly the same, except that it will move it in the minus 1/2 direction. And the multiplication between 2 points, let's say we have 2 points x and y inside the cotangent bundle, we're going to be able to compose them, right, in the following way. You take x and y, you move x e to the minus 1/2 cj of y. So you use the group element associated to this point y, and we use it to move x, let's say, backwards in time by 1/2. And then we use the same expression, the group element for x to move y. And now these two elements of the cotangent bundle, they will lie in the same fiber. Oops. They will lie in the same fiber of the usual cotangent bundle, and we can add them. And this is the T star M addition. Okay, so the picture that you should have in mind for this. Oops. So the picture that you should have in mind is that we have the cotangent bundle, we have the manifold M, and each point in the cotangent bundle is has an associated source and associated target. And if we really wanted to, we could consider just the projection down to the base, but that projection is not part of the structure. So the source and target maps, they are submersions which foliate this manifold in two foliations. So these are the S fibers, and these are the T fibers. And then we have the zero section, which basically are those are identity elements. They represent arrows which go from a point to itself. So so in conclusion, what we have is a holomorphic symplectic manifold, okay, with an additional structure of a groupoid, the ability to compose elements of this space. And that composition involves the toric structure, and it also obviously involves this R matrix, which we chose. And the nice thing, and this follows from all of the study of symplectic groupoids by Alan Weinstein and his students, especially Ping Xu. The point is that if we push forward the canonical symplectic form down to the base by S or by T, we get the Poisson tensor. The Poisson tensor that the R matrix determines. I use the toric structure in order to obtain my holomorphic Poisson tensor, which will be toric, okay, and also to to describe the groupoid, So in the toric case, the groupoid has a very simple structure. This holomorphic symplectic structure is really just the cotangent bundle, but in order to get the additional maps, in order to get the additional structure on the groupoid, we can use the toric action to simplify kind of the way the groupoid looks. Okay, so this whole setup, this replaces, let's say, the holomorphic cotangent bundle that I was talking about before. So, right, and right. So, right. And well, okay, so let me give a kind of feeling. The problem is that I'm not really able to give as much detail as I'd like, but let me give you a feeling for what this has to do with generalized scalar metrics. What does this weird space have to do with generalized scalar metrics? So the important thing is this, that suppose that I had a cross section of this space. And suppose that this cross section was C infinity. Okay. This, when I say cross section, you have to ask, is it a cross section of the S map or of the T map? The answer is it has to be of both. It has to be what's called a bisection, which is a open condition. And the interesting thing is that because it cuts across a holomorphic foliation, it gets an induced complex structure. And because it cuts this holomorphic foliation, there's two holomorphic foliations that it cuts across, it inherits two complex structures, I plus and I minus. So we get two complex structures, I plus and I minus. And these complex structures are not equal, they're not the same, because of the fact that this is not a complex submanifold. It's just a smooth submanifold. Okay. And then what we could do is we could require that this is a imaginary omega Lagrangian bisection, just like we did in the Kahler case. Okay. And as a result of this condition, so the fact that let me call it L, if L is a C infinity imaginary omega Lagrangian bisection, this will imply that if we take the real part of omega and restrict it to L, and we take its 1,1 part with respect to I plus and combine it with I plus, this will be exactly the same as if we take the real part of omega restricted to L, 1,1 part with respect to I minus and combine with I minus, and that will be equal to G, the generalized Kahler metric. In general, if we hadn't made that assumption that it's an LS bisection, if we hadn't made Donaldson's assumption, then these would give two different symmetric tensors, which may not agree. But it's because of the Lagrangian condition that we get a it's the same metric. Okay. Yeah.
So if you took the zero section there, you have the horizontal, and you get back the original.
Okay, so this is part of the detail that I didn't really have time to elaborate, but so actually, if you were to restrict this thing to the zero section, you would get 0. Okay, this is the analog of the actual holomorphic cotangent bundle. It's not the analog of the twisted one. So in truth, what I have to do is twist this thing. So we need a twisted version. And these twisted versions, they have a name, they're studied, they're called morita equivalences. Okay, so let me just explain it briefly. So if you have x with I plus and sigma plus, a holomorphic Poisson manifold, and if we have x I minus sigma minus, another holomorphic Poisson manifold. Okay. Each of these holomorphic Poisson structures, if it is well behaved enough, it will have one of these holomorphic symplectic groupoids associated to it. That's the purpose of this huge subject of study that in Poisson geometry, we have groupoids. I'll call them G minus. This is the source and target of G minus. And this will have G plus. And what I just described is the precise structure of G for that toric Poisson structure. Okay. And the idea is that two different holomorphic Poisson structures can be related by a span like this, where this is holomorphic symplectic, and this groupoid acts on the right, and this groupoid acts on the left. What I mean is that the two actions commute. The fibers of these two maps are symplectically orthogonal with respect to the symplectic structure here. This is what's called a holomorphic symplectic morita equivalence. The idea is that, the idea is that this is the natural notion of equivalence between holomorphic Poisson manifolds if you want to go one step beyond just isomorphism. Like instead of saying that the two holomorphic Poisson structures are isomorphic, you could have a weaker notion of equivalence, which just implies that the groupoids are equivalent as stacks, and that's what you get. This is the notion you get. So this symplectic structure, if we push it forward here, you'll get minus sigma minus, and if you push it forward here, you'll get sigma plus. Well, this is the relation. That's all I can say. Yeah, pi minus lower star omega inverse is equal to minus sigma minus, and oops, sorry. Yeah, and you get this condition. So this is, this is the situation. So this Z space is the replacement for T star F. And that's pretty much, that gives me everything that I need to explain. So this Z omega, this plays the role of what we saw before as T star F. And it plays the role of the Kahler, of the generalized Kahler class. It is the isomorphism class of this space as a holomorphic symplectic morita equivalence. Okay, there's a notion of holomorphic symplectic morita equivalence. It's a relation between two holomorphic Poisson structures, and it has an isomorphism class. And that isomorphism class is the generalized Kahler class. That is what should be the generalized Kahler class. The generalized Kahler class, we should think of it as it has a direction. It goes from one Poisson manifold to another. It's not an element of a group. It's an arrow in a category. It goes from one location to another. Okay, and bisections, LS bisections of Z omega, these correspond to actual generalized Kahler metrics in this generalized Kahler class. Okay, and And then you have the notion of composition, right? So if I have, x0, x1, and x2, if I have a generalized Kahler class relating these two and another generalized Kahler class relating these two, then I can compose these Kahler classes, right? And I can produce Z01, oops, sorry, a fiber product over X1 with Z12 mod the action of G1, okay? And this will be Z02. This is the composition of generalized Kahler classes. This is the composition law. Okay. And right, so this is the structure that generalized Kahler classes have. Okay. And maybe I think just have another couple minutes and I'll finish. So the picture now is going to be that that if we have a generalized Kahler structure, okay, so we may interpret Z as a space-filling brane in the imaginary part of this groupoid or the imaginary part of this groupoid. It doesn't matter because their imaginary parts all coincide. They only differ by this magnetic deformation by a real part. So what we end up with is a single symplectic groupoid over the manifold with the imaginary part of the Poisson tensor. So this is the key object. We take the imaginary part of the Poisson tensor. This is a real Poisson manifold and it has a real symplectic groupoid. Okay, and then in this symplectic manifold, we have a space-filling brane. I'll call it B. And we have a LS bisection, L. And we can try to compute the homomorphisms in the A model of G between L and B. And then we can do what we did before and take convolution of these things. And the point is that when you take objects in these spaces and you pass them through this symplectic reduction, then because of the fact that these are all, because of the non-trivial groupoid structure that is involved, it implies that there should be no reason to expect that this algebra should be commutative. In the cotangent bundle, the addition structure or the groupoid structure is abelian. It's a bundle of vector spaces. In this case, it really isn't. These groupoids are actually moving points around and they involve the diffeomorphism group. And so they're very far from being abelian. It doesn't even make sense to even consider that. And so as a result, this is a ring constructed from a category by using objects. And whenever you produce a ring from taking Homs between objects in a category, there's no reason why you should expect it to be commutative. And that's exactly what happens. So we implemented it for the toric Kahler case. So for toric Poisson varieties, this R, I won't bother writing it out. This becomes a non-commutative algebraic variety. So these are, you could think of them as being like, just in the same way that you think of toric varieties as being compactifications of the complex torus, you could think of these rings, these graded homogeneous coordinate rings, you could think of them as being compactifications of the holomorphic non-commutative torus. And that's what you get from this particular construction. Okay, thank you for your attention. And let's also applaud all of the organizers. I think it was a great success for a first try in doing things in person.
Thank you very much for your talk. Are there further questions? Yeah, Westy.
My father told me that that I should tell the audience that the only thing that lies between the only thing that stands between you and your flight home is your questions. Yeah, so if you have two generalized scalar classes, they must have a source and a target. So if they have the same tip to tail, like if they agree that the tip of one agrees with the tail of the other, then you can compose. But in general, you may not be able to compose. Yes, yes, it's what they call, they have a technical term for this. It's called a Picard groupoid. It's a category where every arrow is invertible, and there's a, I can't remember, there's other axioms, but yes, it's very close to being a group, but the problem is that there are many holomorphic Poisson structures that these arrows go between. It's not just one. In the Kahler case, it's all happening over one complex manifold, and the complex structure never changes. So it's just arrows going from the complex structure to itself. That's how I think about it.
Are there further questions?
I should have offered to repeat your question.
So yeah, so in this last statement you make, the underlying manifolds are Kahler, is it right? You're on a Kahler toric manifold, but you're looking at a GK metric on it.
Yeah, I'm just deforming the Kahler structure to a generalized Kahler, but that deformation gives me a symplectic form. It's a symplectic type, right? And then I'm deforming it twice, 3 times that, 4 times that. I'm deforming it so that the symplectic form gets multiplied by n. And I'm considering the collection of all of those together.
To construct this R.
Yeah, correct, yeah.
And out of curiosity, I mean, I don't know, like does the Poisson structure somehow, is it somehow visible in this R?
Oh, in the ring, you mean? Yeah. Well, it's, you could say that, you could say that you could do this whole construction in families, I suppose, by taking the R matrix and multiplying it by T or by H bar. Okay, and then what happens is that the foliation by these two foliations, as H bar goes to 0, they kind of line up and they just become the usual cotangent bundle. So it's a deformation of the ring, of the usual commutative ring. And if you compute the first order change, it's the Poisson tensor. So it is a non-commutative deformation of the usual Kahler variety.
So quite visible.
I only hope that we can do this for other examples besides the toric ones, which is very challenging. It's because no one wants to tell us how to compute Homs between Lagrangians and space-filling branes. The physicists, they refuse.
Thank you.
There are further questions? Yes.
Yeah, I have another question. So
Yes.
I'm Vicente. Hi. So
Hi.
In this language, what would be the generalized Kahler potential?
Ah, okay, yeah, thank you.
Is there
this
nice?
LS,
Yeah.
the LS bisection, that is Lagrangian for the imaginary part of the symplectic form on the groupoid. And that Lagrangian submanifold is the Kahler metric, is the generalized Kahler metric. And if you want to deform it, you just use a real function, just like you deform any Lagrangian submanifold. And so in a way, just as in the Kahler case, there isn't a single potential, there isn't a global potential. What there really is a Lagrangian submanifold. If you want to modify that Lagrangian submanifold locally, you could of course add a function, d of a function, right? And then you could, and that's what the generalized Kahler potential is.
Yeah, thanks.
You're welcome.
So this is kind of crazy.
I agree. It's crazy.
So you showed that the Kahler metric is a particular type of Lagrangian submanifold.
Correct. Yeah.
So when I
yes. Yeah. I know that's what you want. Yeah.
I want to say that you lack Kahler metrics are special Lagrangian submanifold in there.
So, okay, I mean, it's very clear once you think of generalized Kahler or Kahler metrics in this way, it's very clear what the Ricci flow is. So there's a normal vector field. Like whenever you have this Lagrangian. Well, that's the thing, is that there really is not a metric on this space. Right. There really is not. However, this Lagrangian has a natural normal vector field on it. It has it. It comes from the canonical line bundle of one of the base manifold, and this normal vector is moving it in the direction of the Ricci flow. So that's what the Ricci flow is. Where does it go? You know, how do you characterize the fixed points? The only way that I know is to say that the normal vector field is 0. That's all I can say. And like at every time, this thing will have a normal vector field, and it tells you where to go. And when that vanishes, then you're done. But there does not seem to be a metric on this space. It really is like a holomorphic symplectic thing. And it's kind of similar, it's somehow similar to like a twistor space. That, you know, we know that we shouldn't ask the twistor space to have a metric. It has whatever structure it has. It has this funny symplectic structure, and yet it gives rise to metrics. That's the flavor that this thing has. In the toric case, it is. However, if you change the Poisson tensor, if you make it into another holomorphic Poisson tensor that's not toric, then the groupoid goes haywire and it becomes a bit complicated topologically. And you need to study it and construct it separately, and yeah. So it's a little bit inaccessible in the non-toric case. Yeah.
Are there further questions? Okay, if not, then let's thank again the speaker and also the organizer.